right, just a couple of quick reminders. Your lab number 2 has been released. It will be due not tomorrow, but next Friday. But just don't forget, after your lab number 2 is due, you actually got your programming test 1 coming up, right? Yes. So what I would do is I'm going to, you know what? I might just make it, okay, let me clarify. I might really meant to say the other thing. Beg your pardon. It's good to check together. If you look at the semester calendar there, and then according to it, sorry, let me just refresh it. Yeah, there we go. So that's your semester calendar. Your programming test number 1 is actually coming up. It will be not tomorrow, sorry, not tomorrow here, and then it will be in about 2 weeks' time. So by the class next Tuesday, I'm actually going to give you some guidance about how to get prepared for programming test 1. But I think your best preparation is to make sure you understand everything in the lab 1 solution, make sure how to use Rodin, and I'll be very clear about what might be available to you during the test. I'll just confirm that on the test guide. Just bear with me. I'll do that before the class next Tuesday. And then for your lab number 2, you can see I'm going to release the solution right after the deadline. And I'll definitely talk about it on the Tuesday class for sure to also help you get prepared. And we can potentially maybe schedule some review session maybe on the Monday on that week. So in case you got any question you want to ask me, that's fine too, right? It's a programming test, not really a written one. So we can hold some brief review session in case you got any doubts. We can try to address it. And today, I'm definitely going to dive into many relational operators. You'll find them very useful and relevant to your lab number 2 as well. So I would suggest, once we cover many of the relational operators today, struggle through with the lab 2 a little bit more over the weekend. Next Tuesday, I'm going to discuss a little bit about your lab number 2, just to give you some ideas how you can get through some difficult parts. Lab 2 is definitely an interesting problem to solve, the celebrity. And there will be some variants to the celebrity problem in the subsequent lab as well. So just make sure you do this simplest one properly. So later one will be easier. All right, so apparently on my notes, I definitely made a typo. I really meant to say programming test 1. All right, I'll release the guide next Tuesday. And there's also something I want to bring your attention. So we do have some remote TA support for those of you who hopefully just want some additional support beyond the scheduled lab session. I think we have some limited hours available. So let's see how that goes. I put 2 TAs, their contact information on the e-class. You can feel free to reach out to them. So they are working people. But they completed the same course a few years ago. And they're very good. Very good students, very understanding about the course contents. Feel free to reach out to them and schedule maybe some Zoom meeting with them as well if you need it. We'll see how that goes. If you don't need it, that's okay. If you need it, use it. Any questions about the general rules about the course? Okay, let's have a quick recap as usual, and then we'll dive into relations. So last time we revisited or elaborated on the discussion about postcondition, right? You really want to be clear about what does it really mean. When I say a postcondition is incomplete, right? Especially when I got these 2 together, they will be considered as complete. But what about just one of them in isolation? One in isolation or the other one in isolation? Yeah, just revisit the discussion. That'll be very important. And then we talk about a different way to specify the same postcondition just without using the set operators. Right? You want to get used to it too. Okay, and we discuss about using the choose operator. We'll do that, we'll use it again today when we figure out how to construct relations. That will be the first topic today after the recap. Are you guys okay with the choose operator? Okay. And if you ask me, am I going to ask you interpretation about a choose operator for the exam or test? Not really. But I think it will be nice, since you may have to use that operator anyway for some questions, it's better to understand them more thoroughly than otherwise. Right? All right, and we'll talk about how you can construct tuples. This will pave the foundation for constructing relations. We'll see. And just remember the notation is using the cross product or Cartesian product. And that's one way to enumerate the cross product. And this page is really important, right? We talk about the relation. Just remember, it's a set of order pairs. The principle here is really important, right? And then later on, we're going to talk about a function, a partial function, many other terms. They all to do with relation. Right? Just remember, set of order pairs. And then we talk about the minimum and the maximum relation for any given sets, S and T. If you want to construct many relations among them, just remember what's the minimum and what's the maximum. It will be the empty relation versus the maximum, which will be the cross product. Okay? And we're going to talk about how to construct relations in between. That's also important. We'll get there very soon. Actually, now. All right? Do you guys have any questions before I move on to constructing relations? Any questions? All right. That's good. Okay, let's now talk about constructing relation. And if there's any step that doesn't make sense to you, stop me because it is so important. Otherwise, you will also be struggling with understanding function. Okay, we talk about relation. Okay, and you're given two sets, S and T, like what we did last time. Okay, so now we talk about the set of all possible relation S and T. What do I really mean by set of all possible relation? We know already. Oh, let me show you the second question here. There is a symbol for the set of all possible relation. Let's learn that symbol first. It's not just a single one, but all the possible relations. So it's S double-headed arrow T. So this contains all the possible relations, not just a single one, the set, right? And let's be even more precise over here. Each member in this construct over here is a relation. Meaning that each member is a set of pairs. This is important, right? You don't want to get confused. Let's see some example here. For example, it would not be correct if you say something like this. If you say empty relation over here, oh, you know what? Let me say this. I'll get to be empty. Empty is a bit special case. It will be correct to say the empty relation is one possible relation between S and T. That's a minimum one. So I can say it's a member of S relation T. So this will be okay. Okay? And what about the maximum? The maximum will be the S cross product T is also a member of S relation T. Right? Notice that I'm using the membership operator, right? So the member here, exactly the member set of pairs I'm talking about. Right? Just be careful about the type. Let's do another example. Let's find somewhere in between, and then we're going to figure out all the possible relations. Another one could be, it's going to be a set of pairs, right? So let's say this. Let's just use S and T here. Let's say this is S, this is T. Let's say this is S, and this is T. Let's say. What will be another example? I can say maybe A2. Agree? It's a singleton set. It's a relation containing only one order pair, which is completely fine. That one will be okay. All right? And etc. Okay, we're going to get to enumerating more systematically in just a moment. And let's now talk about this one here. And then I will give you some equivalent expression in a moment. Let's try to figure out all the possible relations on between these two sets, right? The order does matter. So here we say S relation T, by definition, is going to be a set. Every member there is a relation. So I'm going to say this is equal to a big, big set over here. Okay, big set. The smallest relation in there is the empty relation. And the largest relation there is S cross product T. And let's just write them out. Why not? So that one there is a relation of size 8, or cardinality 8. So I'll put it down. A2, A4, also B2, B4. Should be 4. Size 4, agree? Because you got cardinality here is 2. Cardinality here is 2. 2 times 2, 4. So that's good. The minimum, the maximum. Once we get the minimum, maximum, we kind of get a bounce. And then we try to figure out what's in between. This is basically the relation of cardinality 0. And this one here might be a little bit easier to see what we're doing. This is basically a single relation of cardinality 4. Okay? And it's a single relation. In this case, we're basically saying it's a cross product. Let me say that. Okay, just cross product. Yes, question?
Sorry, I forgot what that sign.
Which one?
That sign between S and T.
Between, oh, that sign is a relation. So here, whenever you see this sign here, double-headed arrow, it's the set of all possible relations between S and T. Yeah, so I'm constructing that. So this will be a big set over here, where every member there, this is one member, this is just another member. Every member is a relation. Yeah, so I'm just trying to figure out what are all the members in this set. That's what we're doing. Okay. Yes, go ahead.
How is the Cartesian product between S and T different from that symbol? How do they do the same thing?
So A2, A4, B2, B4. Sorry, what's your question?
So the Cartesian product of S and T,
Yep.
isn't that the same subject of that symbol?
You mean this one here and this one here?
Yeah.
They're not the same. They're different. Okay. So thinking this way. So given S and T, right? This will be the correct relationship between them. Okay. When you say S cross product T, number one, you should understand that this is simply a set of pairs, which is something like this. It's a set of pair. By definition, if you got a set of pair, it's a relation, a single relation. Okay? So this guy here is a single relation. All right? And then when we are talking about this guy here, S double-headed arrow T, or S relation T, this one is not a single relation. It's a set of all possible relations you can construct from S and T, right? So now the correct way to comparing this would be is a member of. Okay, but I'm glad you asked. That's good. It's important to clarify. Okay, so we got basically relation of cardinality 0 all the way to relation of cardinality 4. What's really missing is we need to figure out what are the relations of cardinality 1 and what are the relations of cardinality 2 and 3, etc., right? 1, 2, and 3. Okay, let's see. For the very first one, let's do in detail. And there's a different example on the slide, which I'll encourage you to also try out. You can also see the solution from the slide. But let's do this one here. So we got 3 more categories. Okay. And then over here. Okay, let me put a little bit better. Okay, good. So in the second row, we're going to put the relations of cardinality 1 and also relations of cardinality 2, and finally relations of cardinality 3. That's what we ought to do. All right? Are you guys okay with the structure right now? It's important to see the flow before we get into detail. All right? Before we enumerate out this guy here, can you take a guess, or take an educated guess? How many relations should there be of cardinality 1 based on S and T? How many? If you're not exactly sure, I'll point to you. Give me a moment. If you're not exactly sure, now that you already know what's the maximum, right, caused by which is cross product, any relation in my draw cannot be more than this. So maybe start with that. From this one here, how do I know what are the possible cardinality 1 relation? How many are there? 4. How did you know it's 4? Yeah, in some way, you're basically talking about how to construct the Cartesian product, right? Well, another way to put it, I agree, it should be 4. We're thinking this way. We know that this is the maximum possible relation that we can construct from S and T. If we want to construct a relation, all the relations of cardinality 1, we can just choose one pair and make a relation out of it. Or we can choose this one here and make a relation out of it. We can choose this one, or we can choose this one. Now, how many choices are there? 4 choose 1, basically. Out of the 4 members in the maximum relation, we choose 1 and make it a relation separately. Okay? So this one here is going to correspond to 4 choose 1. And you should really understand the 4 over here is really the cardinality of S cross product T. And the 1 here is really corresponding to cardinality 1 that we are talking about, right? And this one's not difficult to write down. Let me write it. The first relation is going to contain the first pair, A2. And notice that it will be wrong if you don't really have the curly brackets over here. That's not a relation, right? We spoke about that briefly last time. What about the second relation? It would be A4. And the third one will be B2. And the fourth one will be B4. So we got 4 of them. 1, 2, 3, and 4, which correspond to, if you calculate the choose operator here, is simply going to be 4. Right? They are corresponding to each other. That's the first one. Okay? Question? Yes?
For the empty set, right?
Yeah.
What's the difference between just writing the empty set and then curly brackets empty set?
It will be the same. So the question was, would it be okay if I write over here, let's say this guy here, rather than this, can I simply write this? Absolutely. That's fine too. They're equivalent. I think in Rodin, you have to write the curly bracket ASCII first. You'll be turned into this notation.
It's the same similarities for empty set but within curly brackets. So with the set of the empty set.
You mean, oh, okay. Are you saying this? Ah, okay. Interesting question. Okay, that's awesome. I'll put it aside. Interesting. That's in the side note. You can write it too. Okay? Now, guys, your classmate's question goes like this, which is brilliant. Can I say this? I know that this is a relation, as we said. Check. What about this? I wrap it within curly brackets. Okay? That's a question, first of all. I heard no. Anybody want to explain no? Why no? Yeah, one is it's a set of empty set, right? Yes, exactly. The type is actually not compatible. I tell you why. Thinking this way. By definition, if it's a membership, right? This guy here is a set of all possible relations, which boils down into a set of pairs. Now, is this a set of pairs? Not really. So that's why it's not right. Okay, good question. I like it. Not really. Yeah, one more. I think it might be also worth noting, and then I'm almost done with this construction. I may not enumerate all of them. That could be left to you as exercise. They are not difficult. So I want to say one more thing. So when we talk about this guy here, I think it would be nice to say this. The set of So if you really want to think about this notation here, it's really a set indeed, and it's a set containing sets of pairs. That's why this one here wouldn't work. Okay, good. If that makes sense to you. So this part here is really talk about relations. All right, let's now move back to, let's say, this guy here, this row. We want to figure out all the relations of cardinality 2. I'll give you just one example, right? One example could be, let's say we choose A2 over here, and also we choose A4 over here. That could be one example. And then, How many do we have, though? How many? How do we calculate it? 5? 6. Yes, 6 makes more sense, right? Okay. So your classmate was right. The idea would be, if you want to think about constructing all the relations of cardinality 2, think about, you're choosing from this maximum relation, which is of cardinality 4. And then you're going to choose 2 of them from there and make a relation out of them, which is what I did. And then choose another 2 members here, wrap it around, make a relation out of them, and etc. Okay? So how many? As you said, 6, but I'll write it down. So this will be basically 4, because we got 4 members in the cross product, and choose 2 of them and make out a relation. That will be exactly 4 times 3 divided by 2, which will be 6. That's exactly right. 6. I hope we are fine, right? Okay, a final row. This row, I don't need to give you any more example, right? And for this one here, we can simply calculate. This one here will be 4 choose 3. And I'm going to put here, so that will be 4 choose 3, which will be as if 4 choose 1. That will be just 4. So overall, what we have is, and this one will be as if we say 4 choose 0, right? Just 1, no members to be chosen. And this guy here will be as if we say 4 choose 4, which will also be 1, only 1 Cartesian product. So overall, you can do 1 plus 1 plus 4 plus 6 plus 4, whatever number that would be. That will be the cardinality for the whole relation. You can add the number up. That's okay. That's how we construct systematically a relation, right? Of course, you can fill out the gaps yourself. You can see the example in the slide that can give you some more hints. Now, another question for you, right? Knowing how to do this in detail is important, but now we want to somehow draw this construction here to something we learned earlier. How do you see this construction process related to the power set idea? How do you see that? Because that's kind of by definition what this symbol really means. But I didn't really tell you right away. I wanted to just construct this one first to know the process, and then you try to see if this particular process here is indeed somehow calculating the power set of something. right? So we're calculating the power set of what? S cross product T, right? That's really what we're doing. Think about it, right? So the final conclusion for this page. Whenever I say S relation T, it's synonymous. It has the same meaning as, you can say equal to the power set of S cross product T. That's a very important equality for you to know. It all starts from knowing what's the minimum, what's the maximum, and then from the maximum there, you're basically thinking about choosing different subsets from there, and each one of them will be a relation on its own. All right, that's something you want to think a little bit more. Okay, so let's go back to the slides. I believe I said everything, but let's see if I missed anything. If you go back to the slides, a relation, a set of ordered pairs, and then minimum, maximum, just an example, right? That's something we already understood from last time. And set of all possible relations, which we just illustrated. Let's see. We use a power set, right? I didn't really tell you in the beginning, but now we appreciate it a little bit more after we've seen the process. Right? Power set of S cross product T. Each member in there is a relation, and we talk about it. And then, so here, how do you declare? Let me now go here. So what we know is this. Given S and T, right? Some concrete sets. And then we say S relation T equals power set of S cross product T. That's a result we gain. And now, in rodent, now you will know a little bit better. What does it really mean? When you say R, a variable, colon, S relation T. This is to say, R is a member of all the set of possible relations. That means R is a single relation. Okay, I'll say a little bit more, and then I can take questions. This symbol here in rodent is really corresponding to the set membership. Okay? And when you say something like this, you can also say something equivalent. You can also say R is power set of S cross product T. Because we know these two expressions are equivalent, right? You can say either. So by declaring R to be this or R to be this, you're saying the same thing. R is a single relation in both cases. R here, also R here, the same thing. R is a single relation. Of course, in some cases, you might find it necessary to say R is maybe a this subset of. It is a valid expression to write in rodent, but it means something completely different, right? It is not saying R is a single relation. It's a set of relations, different, okay? You may find it useful sometimes, but I'm just saying you should really know what you're writing. That's my point. In this case, R is a set of relations. Okay, different. Good. All right, and then, you can use either way, but I would say typically you might just go for this one. It's a shortcut, right? This you can think about this double-headed arrow is a synthetic sugar for this power set cross product, but I should know both. All right, this exercise is for you. All right, yes, I'll go with you first. On the iPad or on the slide? Okay, sure. Which one? Yeah.
So S and T are sets, right?
S and T, yes. S, T here.
S and T are sets.
Mm-hmm.
set, right? And then empty set, the definition is that it has no values, right?
Yeah, no value, yeah.
So why wouldn't, like, let's say a relation of A and no value not be part of the possible relation of SAT?
Are you trying to say, okay, not exactly sure. So are you saying, what do you want to write? You want to say empty set is a subset of this?
So if empty set is a subset of S, then empty set means that it just has no value.
No value, yes.
So why can I not write a relation of A, let's say, and no value?
A relation A of no value?
A relation of A, and then no other value.
You know what, how about this? Why don't we talk about your suggestion maybe after class? Let me digest that a little bit. Maybe it's my understanding problem, right? Let me understand first, and then I'll share if anything to be shared next week, okay? Thank you. Please approach me after class. Okay, good. Yes? Yeah,
Like, I'm not sure if I wrote it down correctly.
sure.
but,
Which one?
Is there not going to be a repetition, like when we have like AN2 and AN4, like?
No, we don't have any repetition because you can see here, this will be this is an empty set, right? Just by itself. So these 1, 2, 3, 4 here, there's no repetition because each one of them is a relation on their own. So there's no repetition. When you say repetition, what do you mean by repetition? Not really. So here, okay. So let's say this one here, for example. Okay. So here, this row over here would be all the relations of cardinality too. Okay? To really figure out how many there are, we use a choose operator. And by definition, the choose operator is not going to repeat. It tells you there will be 6 of them, right? So for example, 1 here, 2 here, and 3 here, and etc. So when you choose each one of them, you're not going to repeat. When you say repeat, what do you mean by repeat? You mean the choose operator is going to include some repetition, or?
Yeah, I meant like, you can have something like, if we have AN4, we can have AN4 and
No, you cannot. Okay. So if your worry was about, for example, let's say, is it possible that you may have, I'll just draw that in temporarily. Is it possible I got this one here as well? I got A4 and also A2. Is it possible these two are counted twice? No, it's not possible. The way we actually use the choose operator over here is going to make sure, remember the choose operator is going to be 4 times 3 divided by 2, right? This 2 over here, like what I explained last time, is going to make sure whenever you got these 2, even though they are, if they appear in different orders, they could be different sequences. But as far as a set is concerned, you got to divide it by 2 factorial to get rid of the duplicates. So they will not appear in the same set over here. Does that clarify your concern, or? Okay, yeah. Okay, so if I understood your question correctly, if you're worried about repetition, this is what you should do. The choose operator itself, by its interpretation, you're not supposed to include any repetition. So when you calculate this one, 4 choose 2, it will give you the answer 6. What does that mean? That means if you try to enumerate the 6 relations over here, all 6 of them will be all the possible ones you can do without any repetition. If you actually have to come up with only 5, that means you're missing one. If you come up with 7, then definitely some of them will be repetition. So 6 should be just what you need. Yeah, the formula. Okay. Yeah, if I haven't answered you completely, please reach out to me again. Maybe I'm not understanding completely. Okay. Okay, let me move on, but keep interrupting if you need to. All right, so now this exercise here, just slightly different S and T. I will let you do that, right? You can enumerate all the
There is a
typo?
if you go back to the notes,
Yes. The notes or iPad notes? Of course.
there should be a column between R and also this one. That's a period.
This one? That's a colon, right? Maybe I didn't write that pretty, I guess. I definitely meant to say, call it. Yes, no worries. Thank you. Yeah, it's good to be clear. All right, let's now move on. All right, so that's the exercise you can try. Yeah, guys, give a try on this exercise over here, but that one there also shows to you how you can enumerate all the possible relations, right? The dot, dot, dot here is something you can try to enumerate in the middle. Okay, now, finally, we can now talk about the various relational operations. That's good, okay? That's something we'll do. Why don't we do the very simple one first, just for a few minutes. It wouldn't take long for the first few. And then we take a short break, and we'll do the more complicated one after some nice fresh break. Oh, I do have some good example here to assign as exercise for you. Okay, I will do that, and then do some simple relational operation. 10 minutes, and then we'll take a break. So this will be some exercise for you to try to enumerate relation. Exercise. Okay, so now let's say we got departure CT. It's a set. You think about it, say a carrier set. And then we got Toronto. And we got Montreal. If you don't mind, I'll only put Canadian C. Vancouver. 3. And then we got destination. Okay, for now, I'll just put, how about Beijing, and then Seoul in South Korea. Doesn't matter. You can change the name as you wish. Doesn't matter. Do you know where the city is? Penang, Malaysia. Okay, doesn't matter. You can change that. No worries. Hey, let's say we got departure, destination, and what I want you to try is, if I say airline is going to be a member of departure relation destination. Apparently, when I say this, I'm saying a particular airline, could be Air Canada, could be Delta, they are going to support a subset of the Cartesian product. They may not support all the combination. They may, but they may not, right? They can be all the possibility from different spectrum, right? And my suggested exercise will be, try to see if you can enumerate. Number 1, what's the cardinality? Number 2, you may want to enumerate. I will do number 1 with you. How about that? Guys, what's the cardinality of this? What's cardinality? Two to the power of 8?
To the power of
3? Are you sure?
No.
No. You're taking a guess, or why 6? Well, shouldn't that be 9? Okay, let's see. Okay, so this one here, by definition, is the power set of departure, cross product, destination, right? That's what we said in the last page. And what will be the cardinality of this? What's the cardinality of that? 3 times 3, right? 9. Not 3 plus 3. Maybe that's what you did, I guess, right? All right, 9 here. And then, what about the cardinality here? It will be 2 to the power of S cross product T, right? You can look up to what we said earlier. That will be whatever, 2 to the power of 9. You know how to simplify it. 512, I believe, right? Are we okay with question 1? All right? And for question 2, please try to enumerate a bit. You don't need to exhaustively enumerate, but you should really at least try to see if you can really get an idea about systematically enumerating them out. It's important. Okay, I'll suggest we do just the first set of relational operators very quick, and then we'll take a short break. Okay? If no more question here, let's now move on. Okay, now let's now talk about, domain, range, inverse. Pretty easy, but there will be some nice algebraic property that we can learn about it, and it will help for later. Let's do them quickly. And one thing to note, if you look back to the slides, every relational operator, because each relation by definition is a set of pairs, so it makes sense when you want to define operators on a set of pairs, you're going to use set comprehension notation to define them. So you got lots of exposure to set comprehension. This is the relation that we're going to use as a running example, right? So you can think about R. The first value here is A, B, C, D, etc. And then the second one is numerical, 1, 2, 3, 4, etc. Okay? Or you can think in this way. R here could be just a member of, it could be alphabet, relation, maybe integer. Right? R is a single relation, right? That could be how we declare its type. All right, easy for each one of them. So when we talk about domain, for this one, I'll refer you back to the definition on the set comprehension notation on the slide. The domain is simply just going to be the collection of all the first value in the pair. A, B, C, A, B, C, D, E, F, and make a set out of them, which will be A, B, C, D, E, and F. No repetition, of course. Right? That's a domain. Easy. The second one is about range. By definition, it's kind of symmetric. It's going to be all the second value in the pairs. 1, 2, 3, 4, 5, 6, 1, 2, 3, and make a set out of them. 1, 2, 3, 4, 5, 6. That's it. Right? Domain and range. Second values. And of course, I will encourage you to also look at the formal definition using set comprehension. They are easy. And what about inverse? R here, inverse. I'm pretty sure you saw the inverse in lab number 2, right? In case you don't know what it is, now you will know. Right? If you look at the definition on the slides. Oh, by the way, so for every relational operator, you will also see the ASCII syntax. That's what you have to type in Rodin. Okay, just notice that. And for the inverse, in some way it's very easy. That is to say, if you got a pair D R prime in the relation, what should be the member to be included in the resulting set in the inverse? Well, it should be R prime D, just reverse the domain and the value, right? That's by definition. And let's now try to enumerate them just for completeness. Reverse them, so that'll be 1A, and then 2B, etc. 3C, 4A, 5B. I'll only do it once. 6C, 1D, 2E, 3F. That's the inverse. Very easy. But we can consider something that's going to require more insights into the understanding of these operators. Now, I want you to compare R, a relation in general. R may be a relation like this or any other relation, right? So we're considering R and its inverse. How do we relate their domains and ranges? So this one here, of course, would be R inverse. So we talk about the domain of R, the range of R. We also talk about the domain of R inverse and also the range of R inverse. These four, how do we relate them with each other? Based on what we knew over here. Anybody? There are at least two properties we can say. Why don't we go with you? Go ahead. Yes, I agree. For example, here, domain of R would be domain of R would be here, exactly here. And the range of the inverse would be A, B, C, A, exactly here, right? Let's make it set, right? So this will be what you had to say. Domain of R is going to be equal to here, and then here. And for the other one, you can try to convince yourself, right? Domain is range, range is domain. And we call these algebraic properties. And we'll see more. Algebraic properties really try to put several operators together so you can get some insight about how they work together. We'll see more. All right. Any questions? Yes. Okay, good question. So for example, over here, relation by definition is a set of pairs, right? It's a set. So now, if I got another relation that's basically the same, except I might say B2 over here and then A1. And then the rest will be the same. In this way, will they be considered as the same relation? Yes. Because for the sets, the order doesn't matter. Yeah. So always think about relation is just a short form for a set of pairs. Right? So order doesn't matter. Okay. If no more question, why don't we take a short break by taking attendance? Let me stop the recording, and then please schedule. All right, so we spoke about domain, range, and inverse. Let's get to something slightly, not really complicated, but slightly, not as basic. The next one is called the image. Okay, and that's the same relation. We're going to use that as a running example, but let's see what's really, how do we call it? We call it relational image, which is image. And it's an operator that's going to take a set. All right, it's going to take a set. And what it is going to return is going to be a sub-range. It's not going to return a single relation. No, it's going to return a subset of the range of the relation. Somehow we say it's mapped by S. What do we mean by that? We're going to see the formal definition. So this will be the formal definition. I'm going to apply that to use on the example, but let's all read it together. And this will be what you have to write, like a square bracket, a little bit like an array notation. It's just that the index now is not just a single integer. It's more like a set, right? Thinking that way. So when I say I want to get the relational image of the relation R over a set S, that's how we read it on the left-hand side. Okay? It's going to be, number one, a set. Every member in the set is going to be a single element. It's not an order pair anymore. So the resulting set is not a relation. The resulting set is just going to be a set of single values. What's R prime? So this will be the constraint on the R prime. We say that over here. So here, number one, the dr prime is actually a pair in the relation. Right? And then we say D over here is a member of S. So what it's saying is we want to find out all the pairs in the relation R such that for those pairs, its first value is a member of the S that we're calculating the image on. Okay, that's basically how you read the definition. Read it through maybe a few times if you're not convinced. Let's now do an example, then that'll be clear. Okay. And then I'm going to ask maybe some, let's do one example together, and then I do have some checks to help you understand maybe even more. We'll get there. Let's now calculate this one first. Let's say we got this relation over here, okay? And then let's try this. Let's say we got R image over a set. By the way, is this the right notation? Not really, right? It's not a set, right? Instead, I'm going to put a set here. A, B. All right, so this is the S that we're talking about. This is the little s that you will see in the definition. Okay? Now, by definition, it's going to be a set of R prime such that d R prime is in this particular relation. So that means can be this, can be this, can be this, every one of them. But we are not going to include all of them because there's another constraint, which is the D should be a member of little s, which will be AB. If you only consider this constraint over here, it's going to include all the pairs in the relation. But after considering the second constraint over here, so that means we're only going to include those pairs where the first element is either A or B. So this one here, there's one here, there's one here, and that's it. Right? Those are the pairs where the first element, D, is in AB. But the resulting set is not going to include each pair. Instead, it's only going to include the range value, the second value, basically. Right? So it's going to be 1, 2, 4, and 5. 1, 2, 4, and 5. That's the relational image. Okay? Intuitively, when you're given this, just go to the relation you're given and then try to select all the pairs where the first element is actually either a member in the set. And then instead of choosing the whole pair, you're just choosing the second value. Make it a set. Subrange, right? Just don't forget the term. It's a subrange. So this is actually a subset of the range of R. Subrange. Okay? So we are done with the first question here, right? This one's done, which I just did. Now, question for you. What is the image of this set over here on the relation? What is that? What should that be? Second question. Anyone? Should it be empty? Or you don't think it's really compatible?
No, it's not.
Not compatible, right? Maybe that's why you were silent, okay? All right, well, you might just be given anything in the test, right? You gotta be very clear how you should respond, right? Because whenever you talk about image, there is always the implicit assumption, right? That this little s should be somehow of the type. Oh, how about this? Let me say this aside. Let me put it aside. Okay, I'll put it here. Usually, when you are asking about, let's say if you got R, that's a relation between S and T in general. And then, whenever you're asking about R, image of R on S, so where S is a set, there's always an assumption about a well-definedness, which is the little s is a subset of the big S. So this S here is this S over here. This S here is this S here. Right? That's something you want to keep in mind. So that is why over here, the second question is undefined. Because in order to really get an image on R, the first element is basically alphabet, but 1, 2 is not alphabet, so it's undefined. On the other hand, does it make sense to ask the image of the same set over here on the inverse of R? It makes sense, right? Okay. How do we write it down, by the way? Okay. Let's try. I'm going to say the R inverse and get an image over 1, 2. Okay? That's how you write it down. Now, how do we compute it? Of course, if you are still not feeling very comfortable calculating right away, don't worry. You can always apply the definition here. But sometimes you might, once you get very used to the concept, this one might just slow you down. How would you do that? Here, because we're going to talk about inverse, just imagine that the relation is going to go the other way. 1A, 2B, 3C, 4A, etc. Right? That's R inverse. We know how to calculate it. But now the image is on 1 and 2. Select all the pairs where it involves 1 and 2. It will be this one, this one, this one, this one, right? 1, 2, 1, 2. I hope I didn't miss anything, right? And then what will be the corresponding range value for the inverse? It will be ED, AB, ABDE. Yeah, try to practice yourself. If I make any mistake, please just correct me. But I believe that's right. That's also right on my sheet. Okay, let's now talk about a little bit of algebraic properties to further understand what's going on here. Let's calculate one by one. It does take some time to really, to think about the answer. So in some ways, it's not really fair to ask you to think on your feet. But do your best, right? If you can think about something, feel free to suggest. Now, I want you to try the following. I want to calculate the range of R. Is it possible to define the range of R in terms of some image? Is it possible? Okay, if you say yes, I agree. Let's now see what it looks like, right? Again, you can, maybe once you have seen this, it kind of makes sense to you. How do you practice? Maybe when you go back home, once you forget about everything, try again to see if you can come up with the same answer. That might be the nice way. Okay, I'll give you the answer. Now, I want to say the range of the relation R, any relation R, is going to be equal to the same relation R, but takes the image of what set? Domain of R. Very good. Okay? This is just another interesting, useful, basic algebraic property. All right, similarly, how do we calculate the domain by some image? I'll give that to you. You can think about it. So we will say the domain of R, because the range, the image is only going to give you the range, so maybe you want to inverse it, right? How do we do that? R inverse. And then we want to take the image of the range of R. This one, think about it. And there's a variant to this. Here, you can also replace it by, based on our algebraic property earlier, right? Over here. You can also say that's the domain of R inverse. What I would suggest is, for this one, it might seem a little bit trickier. Apply this to the relation here to see if that's really the case, okay? But if you can think abstractly, that's also good, even better. All right, any question? Yes? Sorry, say it again? Duplicates? No, the range is supposed to be a set, so it cannot contain duplicates, no.
So in the first example,
Yeah.
if we had an ordered pair that was A and then 6,
Mm-hmm. If you got A6 in the relation, you're saying, that'll be okay. So let's say hypothetically, when you construct a range from a relation, all the duplicate on the range or domain will be removed, actually. For example, maybe this is what you're confused. When we calculate, let me see, 1, 2, 3, 4, 5. Okay, good. When we talk about the range of R, right, it's going to be 1, 2, 3, 4, 5, no duplicate so far. And 6, and now 1 is duplicate, so it will not be counted. 2 will not be counted. 3 will not be counted. So range will just be 1, 2, 3, 4, 5, 6. Right? All right, we got 30 minutes. We can do more. I would suggest we do at least the restriction and subtraction, at least. And the next slide is going to, the next 2 slides are going to tell you about restriction and subtraction. I want to talk about all 4 of them together. It might be a little bit easier. And it will be the best to give you a table to summarize the result, to make it easier. Because the notation can be a little bit weird when you first saw them. Okay, let's now do a summary table here. Let's say, in general, and we'll do an example together. If I got R as a relation, is a member of S, relation T, and let's assume we got little s is a subset of big S. Let's say that's what we're given. And we're going to talk about 4 things together. So let's have a table here. And then let's got another one here. And another one here. Okay, we're going to talk about restriction. We're going to talk about domain and also range. Each one of them, we're going to talk about restriction and subtraction. Subtraction. Okay, it's good to talk about all 4 of them, so you will just be clear about how to put the operator. Whenever you talk about restriction, if you talk about domain, you should really point to the domain. If you talk about range, you should point to the range. Domain should be the first element, right, on the left. Range should be the second element on the right. So when we talk about, let's say, domain restriction, so the arrow should really point to the domain side. When you talk about range restriction, you should point to the range side. Right? You can see one is pointing to domain, the other one is pointing to range. Okay? And then we want to restrict, in the domain case, we're going to relation restricted to some domain S. All right? Also, the relation restricted to some range S. Range T, actually, I beg your pardon. I think it will be better for me to introduce just another set. Let's say T, T. All right, I think that'll be better. All right, so this triangle over here is a restriction. When it's pointing to the right, when it's pointing to the left, it's pointing to the domain. When it's pointing to the right, it's pointing to some range. Okay? Now, what about subtraction? Just put a minus sign. Okay? It's going to be a triangle again, but it's going to be a minus here. A triangle here, but it's going to be a minus here. And then range subtracted by certain set. Domain. And also range subtracted by some range set. So we're going this way here. We're going this way here for the domain. And we're going this way here. And going this way here for the range. Every operator here is going to return a new relation to you, just a new relation. So for example, let's look at one of the definitions. So each of these operators returns a new relation. If you want to use a Java term, it's immutable. By the way, string class is immutable in Java, right? If you say string dot, I don't know, substring, it's going to return back to you a new string, right? Similar idea. All right, so for example, if you look at the definition for one of them, I'll just show you one. So let's say you got the relation domain restricted to some domain value ds. So ds is a little bit like the s over here. Okay? So what you want to realize is this notation here is going to give you another new relation. A new relation separate from T. Sorry, separate from R. And of course, this one here is specifically for domain restriction. And how is that defined? By definition, it's going to be a relation, so each member there is going to be a pair. Right? By the way, I'm using R prime over here because I already have R. That's why. Right? I cannot use R, right? In case you're wondering. And then it's going to be such that dr prime is in R. And also the domain value over here is in ds. But you can definitely look at the definition. Right? But the important thing I want to highlight is when I apply domain restriction, the result is going to be a set of order pairs, which is just going to be another relation. Okay? Let's now do some example. And we might have time to talk about overriding very quickly. And that'll be it. All right, now how do we calculate? Right? Let's do one by one. Number one, domain restriction. R here, R domain restricted to, let's say, AB. I'm going to return a new relation, and all the pairs in the relation has the domain value AB, basically, right? So now I'm going to collect it. A, B, that's it. So it's going to be A1, B2, A4, B5. A new relation, domain restriction. And let's now compare right away what's domain subtraction. Okay, I'll put it here. The third one. Now you can see R here, and then same triangle pointing to the domain direction, but I'm putting a minus sign. It's subtraction. You're going to do something opposite. All right, that means from R, all the pairs which has the first value A or B, get rid of them. So here, I don't want this one here, because you got A, you got B, you got A, you got B. What remains will be what we need. Okay? C3, C6, D1, E2, and then F3. All right, that's about domain subtraction. Let's do range restriction and range subtraction very quickly, right? And that'll be it. That should be good enough for you to understand these. If I give you a new relation, want to calculate a new relation, a new set to calculate these four operations, you should be able to do it. Let's do more. Let's say now we got R here. Now I want to restrict that to be some range. Let's say 1, 2. Which will be, well, similar. Choose all the pairs in R such that the range contains 1 or 2. This one, this one, this one, this one. That'll be it. Make a relation out of them. A1, B2, D1, E2. For completeness, let's do one more. And then we can talk just about overriding very quickly. Okay? Now, let's talk about range subtraction. R here, pointing to the range, but I'm now going to put a minus sign. and then 1 and 2. You're going to somehow create a new relation by getting rid of all the pairs in R involving 1 and 2. It's a second value, right? Get rid of it, get rid of it, get rid of it, get rid of it. It's going to be C3, A4, B5, C6, F3. All right. And of course, I'm showing you what you're supposed to really calculate if you're given a similar question in the test, right? That'll be the fastest way. However, at the same time, you should also, when you study, also look at the formal definition using set comprehension. That's also important, okay? And I got 3 minutes. Why don't we see briefly about the relational overriding quickly, okay? I may not talk about all of them, but at least we can see some definition there, okay? And we can continue from there. Okay, here. And then I'll give you, how about this? I will give you the definition here. Okay, let's see. This problem, I'll leave that for next time. Okay, how about this? Whenever we talk about relational overriding, the best way to think about it is there are two things to be combined together. Let's see the definition. Let's understand just definition. That'll be enough. What's the notation like? On paper, it's going to be R, the relation, and then you have some triangle over here, but it's not minus, it's a sign that's just touching, like that. Okay, in case you don't know how to write it, right? It's not really minus inside. And then it's going to take some set. Sorry, it's going to take a relation. So this is a relation. This is just another relation. So whenever you do overriding, you're taking two relations and do something about them. Let's look at the formal definition, and that'll be it, right? We'll continue with some exercise and some algebraic properties on Tuesday. And most likely we can finish, hopefully, everything on Tuesday. And then, by definition, it's going to be a relation. That's why we got some D and R prime. Such that, okay? There are two parts over here. Part number one, if the pair is already in the T, just included in the resulting relation. This part here is important to know. This T here is the T here. Or there will be another half that we want to include. What would then be? If somehow the relation is in R, but its first value is not part of the domain of T, we also include it. That's by definition. Try to look at this formal definition a little bit more, and then we'll see how to compute it. I'll put it here. This part here is going to be some condition. So we say D R prime is in R, and B is not in the domain of T. Okay, what I want you to see is this, and then we are done. The R here is the R here, and the T here is important, and then we'll talk about not the member of. Okay, on Tuesday, I'm going to start in this definition here. And meanwhile, I would suggest you try to make as much progress as possible on lab number 2, and I will try to talk about it a little bit next time. All right, thank you so much. See you later.